Hello, and welcome to Lecture 2 of Electric Charges and Forces in Phys 1201. And in this lecture, we're going to just explain a few more things using the charge model we developed in the last lecture. And then we're going to see a few more things where we need to extend our charge model down to what we know about the atomic scale. Let's use our new charge model to explain a few things in detail, and while we're at it, we're going to learn to draw charge diagrams. So here's a neutral metal ball, and notice I've drawn it with equal quantities of positive and negative charge. And especially when I'm talking about neutral objects, I'll tend to draw both of the signs of charge in it. Here's a negatively charged plastic rod. I haven't bothered to draw the positives in it, and that's because it's going to remain negatively charged throughout this. So let's talk about why, when we touch this negatively charged rod to this neutrally charged ball, the charge transfers so that the ball ends up negatively charged. So here we go. We touch the negative rod onto the ball. Now remember, like charges repel. Now this rod is full of negative charge, and they're all pushing away on each other. Well, we've just given some of them a place to go, and so they're going to go there. So I'm going to grab one of these negatives and I'm going to move it over. And we're not quite done. We've seen that we can charge part of the rod and the other parts will remain neutral. So apparently charge doesn't move around on it very well. So if I now touch another part to the ball, like over here, then a little bit more charge is going to get transferred. And so this is going to explain both why charge transfers, because it's pushing itself away, and with the rod, why we had to seem to touch the ball a bunch of times. We're transferring charge off of different parts of the rod. Now let's talk about discharging. When we take this rod and we now touch the rod with our hand or to the desk. So here's just something that we're touching the rod to. And again, this thing is neutral, so I'm going to draw both signs of charge on it. Then again, every time this rod touches it, each part may lose some charge. That charge gets transferred over to the other object because the negative charge is pushing the other negative charge, and so some of it is going to flow off to get away from all that other negative charge that's pushing on it. But we're going to have to touch every part of the rod to that other object, whatever it is, to be able to get a lot off. And what we want to do is touch it to a very large object where there's lots of room for all that negative charge to go away. Now here are two metal balls in contact. And I'm going to charge up a plastic rod, and I'm just going to touch it to one of the two metal balls, and watch what happens. After the two metal balls have been touched, now they repel each other. It takes them a little while to settle down, but you see they're repelling each other. They were hanging, touching, and now they're standing out from each other. Now that's interesting because I didn't touch both balls. Also, if I just give them each a light touch with my fingers, it totally discharges them. What just happened is subtle, so let's talk through it. After the negative plastic rod touched just one of those two metal balls, the metal balls repelled each other. Now we know that when charged objects repel each other, that means they have the same sign of charge. So those metal balls must have both been negative after we touched just one of them with the plastic rod. but the rod didn't touch both. So the charge must have been able to move around on the first metal ball around to the far side and get on to the second metal ball. And it had to have done that really fast. In fact, these charge transfers and charge moving around inside objects tends to happen on timescales way, way faster than the blink of the eye. Now let's contrast that with an earlier observation. And that's that when we rub plastic or glass, the rubbed end ends up charged. But the end that we didn't rub remains neutral. We've seen that because the unrubbed end doesn't exert any electrical forces. So while charge moves around easily on the metal balls, it doesn't seem to move around on glass or plastic. And this is telling us that there are fundamental differences between these materials. The other thing is that I could discharge those metal balls by just touching them, just for a moment. But remember, to fully discharge a plastic rod, I kind of had to touch it all over and roll it around on the desk. It took some effort. So this is again telling us there are some big differences about how charge is transported on these objects. What we've just seen is that the metal ball is a different sort of material from the glass and the plastic rods. The metal ball is an example of a conductor. Charge moves freely throughout it. And in contrast, the plastic and glass are what we call insulators. Wherever we put charge on an insulator, it tends to stay there. And for the time being, you can think of conductors as just metals, and basically everything else as insulators. Now that's not really accurate. For example, once we get outside of solids, there are lots of liquids that can be conductors, which aren't metals. But as a start, just think of metals as conductors and everything else as insulators. There's a nagging question we've had with us ever since the beginning of this unit, because we used it in the definition of charge. Why are neutral objects attracted to charged objects? Opposites attract, like charges repel. Shouldn't neutral objects experience no electrical force? Why are they attracted? Well, let's look at this. The charge model will answer this for us, but we need to bring in an additional piece of information. For the metal ball, we know that charge moves around on it freely. And I'll bring in another piece of information here. It's actually only the negative charge in a metal ball, in any metal, that moves around freely. The electrons move around. The positive charges are locked up in the nuclei of the atoms, and those don't move around. Now, as we bring a negatively charged plastic rod, for example, close to the neutral metal ball, it's going to push on the electrons and pull on the positive charges. Well, the positive charges are stuck where they are, but the negative charges can move, so they tend to move away from the plastic rod to the far side of the ball. Now, this is an exaggeration. They really only move a very small distance. But the effect is now that there are two forces acting on the neutral metal ball. There's an attractive force on the positive charges and a repulsive force on the negative charges. But remember that electrical forces get weaker with distance, and these negative charges are on average farther away than the positive charges, so that repulsive force is smaller than the attractive force. So the net effect is that the neutral metal ball is attracted towards this negatively charged plastic rod. We call what's just happened to the neutral metal ball polarization. The metal ball is now polarized. Note that it's still neutral. We haven't added any charge or taken any charge away from it. It still has equal quantities of positive and negative charge. But that charge is now distributed differently so that one side of the ball is more positive and the other is more negative. Now I want you to predict the outcome of this demonstration. I'm going to charge the glass rod. And I'm going to hold it close to the metal ball, but I'm not going to touch it to the metal ball. What I am going to do is I am going to touch the metal ball with my fingers while holding the glass rod close. And then I'm going to let go of the ball, and then move the glass away. I have to do them both very quickly, but I let go of the ball first. And at the beginning of the next lecture, I am going to bring the plastic rod close to that metal ball. Is it going to attract it, or is it going to repel it? In other words, using the glass rod and touching the ball with my fingers, did I just give this ball plastic charge, negative, or glass charge, positive?